Part 3, differential operator. Generalized coordinate. Extrinsic geometry, 3 dimensions. Lecture 14, spherical coordinate. Spherical coordinate is a particular case of the generalized coordinate. Elements of area in R3. The previous vector, we derived the elements of length and volume in R3. Now, from the previous video, lecture part 3, lecture 4, part 7, lecture 12, 13, and 13A, 10KB. This is this development. They are based on this lecture right here. Now, this is a curve. This is a curve here. Okay, theta is a curve. All right. Okay. And this is azimuthal angle. This is polar coordinate, azimuthal coordinate, and this R coordinate. This R, phi, and theta. They are coordinates in the spherical approach. Let's say there's a surface of a sphere. This is a tangent vectors. AR is a tangent vector to R direction. A phi is a tangent vector in the polar direction. Polar direction. You see this direction, polar direction. Okay. And theta, there's a curve here. Theta is a tangent vector to this curved theta direction. Now, ARDR is just the element, the element of length in the R direction. A theta, D theta is the element, this case, is the element of the, is a tangent element in the theta direction. A phi, D phi is a tangent vector in the phi direction. A phi, D phi. Now, this is a, remember that the basis vector AR, A phi, A theta, they are orthogonal, as we showed in the previous video. They are orthogonal. Likewise, the elements are also orthogonal. Now, let's divide step 1 and step 2. Step 1, differential length vector, radial direction. Okay, this is I already wrote here, but this is the definition. The element dr in the radial direction is partial of r with respect to capital R dr. Attention, this is a position vector r. Okay, is OP. Then dr is a. That's a definition of the basis vector. Then, as we did the previous video, the position vector is expressed in terms of the curvilinear coordinate. E1, E2, E3 are the Cartesian, the basis vectors in the Cartesian coordinate. Remember always that EI dot EJ delta IJ. That's a chronic delta. They are orthonormal. So, likewise, in the polar direction, phi, the differential element dr phi is partial R respect to phi d phi. This is just take the derivation of the position vector with respect to phi. then you obtain just this parenthesis over here, d phi. So dr phi, the length element, the vector length element, tangent, tangential, dr, d phi, and the theta, this vector, they are orthogonal, with a tangent vector orthogonal to the surface, to the spherical surface. Now, obviously in r direction, phi direction, in theta direction. It's quite easy, as we did before. So this is a theta, this a y, this a r. That's over here. Now, let's move to step 2. Surface area element via cross product. Okay? The differential area in a given coordinate plane is given by the cross product of the differential length that plane. Okay? Surface element of a sphere. There's a fixed radius. I fix the radius and the vector, the element, you see, will be, in this case, orthogonal to this tangent plane. You have a sphere, you have a plane, you see that we have the vector, the base vector, which is perpendicular to the tangent plane to the sphere. In this case, the radial direction. Okay? Fixed radius. You see, this you see that this area element is given by the cross product of this element dr phi cross dr theta. Okay, this is what we did like here, and this one is right over here. Okay, and so from the calculus, linear algebra, we can obtain the cross product. This is determinant. This E1, E2, E3, and this case, this line here is the component of this vector over here, and this line, the third line, is the component of this vector a theta. Now, I just want to expand this determinant a phi cross a theta. It's just easy. You see, you just cross here, cross there, and this is E1. Then you cross here, cross the column, and cross the row, and then you get E2. Likewise, you cross this row and this column and this row, you get the component E3. This is, if you do this, okay, this is a very easy like a trigonometric relation, expression. You just got, I'll put just the answer over here. Now, the area element is the R phi plane. R phi plane, you have fixed coordinate theta. This is dA theta. This is R d phi dr. This is R dr d phi. See? Now, likewise, the area element over here, okay, fixed phi, just dA phi, that's a magnitude. That's magnitude. You just take this element over here, the cross product, and that you multiply. It will be this times this is equal to this. Okay. All this expression for the length element, they are over here on the step 1. Now you can see, instead of doing the cross product, you could see a very in a very easy way, I will erase, let's see, I will erase, let's erase here. See? You see easily how to obtain this length there. Now, you have, for instance, this curve over here. This is the coordinate, the polar coordinate. Now, look, I write here, this here, attention now, D, R, let's put here. You see, this arc, just look this arc over here. You see, you have the capital R. This arc is capital R defined. Just a geometric viewpoint. This is defined. So I have this length. You see over here. You see over here. This is the area element. Okay. This is r sine phi d theta, and this over here is r d phi, and this element is r sine phi